In 1935, Einstein's pen pal scribbled down a thought experiment that continues to puzzle the scientific world to this very day. And in 1908, a Dutch physicist became the first to produce liquid helium, at that time the coldest material in our known universe. Then, in the 1980s, scientists working on either side of the Iron Curtain unlocked a secret that had been hidden in plain sight for centuries.
I'm gathering that these things are all related.
Well, they are, and they aren't. All at the same time.
Oh no. We're about to enter the quantum realm, aren't we?
Buckle up. Today we are pushing the limits of reality as we know it to talk about quantum computing.
This is Inflection Point.
Spanning a century of reporting from C&EN, this new podcast traces discoveries from our past
to how they shape our present
and will change our future.
I'm Gina Vitale.
And I'm David Anderson.
So, quantum computing, a notoriously easy concept to understand.
Right, yeah, sure. I mean, I figured we'd do a simple one.
Okay. Before we get into this, let's just say neither one of us is a quantum computing expert.
A quantum computing expert. Yeah, I'd love to meet this mythical person. Does such a being actually exist?
It's a good question, honestly. Quantum computing is based on the principles of a field called quantum physics, which is pretty complicated. Even people at the forefront of science are still trying to figure it out. And since the two of us are nowhere near that forefront, we're going to try to keep things at a pretty low level here. Let's start with the most fundamental building block of computing, which is called a bit. David, do you know what a bit is?
Of course I do. It's a small amount of something.
That's kind of close. In terms of classical computing, a bit is basically the smallest unit of information. It is short for binary digit. It can have a value of either 0 or 1.
Right. I was kidding earlier. I know computer.
Right, of course. So that bit that we were talking about, that's in traditional computers, like your MacBook. Quantum computers, in their great quantumness, use a different kind of unit called a quantum bit or qubit.
I'm going to assume the qubit is more complicated than a bit.
Much more complicated. You see, a classical bit can only ever have a value of 0 or a value of 1. It's binary. It's only got those two options. Kind of like a light switch. It can only be in one of two states. In that case, on or off.
I'm following you so far.
A qubit, on the other hand, can be in superposition. This is where things start to get kind of heady. Basically, the system can be in multiple states at once. In the case of the light switch, it could be both on and off. It's like that classic thought experiment with Schrodinger's cat.
Oh, interesting. I didn't know you were a Schrodinger head like myself. I know a little bit about the guy, but of course, continue. Tell us about that famous thought experiment.
There's a cat. Of course, there's a cat in the box, and the cat is alive, but maybe it's not alive. And because you haven't opened the box.
Gina. You are kind of sounding like a fake fan.
Oh.
Luckily for you, this is an inflection point. Let's go back to 1935. Now, if you're with me. In 1935, there were these three scientists who wrote a paper about quantum theory. Boris Podolsky, Nathan Rosen, and someone you might have heard of.
Oh, Schrodinger.
No.
Oh.
The third guy was Einstein. They wrote a paper in a publication called Physical Review, titled Can Quantum Mechanical Description of Physical Reality Be Considered Complete?
Catchy.
This was written when quantum theory was still new. One of the people at the beginning of this new science was Erwin Schrodinger, the cat guy.
Oh, okay, so he was there, right at the start of quantum theory.
Yeah, this paper that Einstein helped pen, if I can simplify it down to just a very basic level, argued that quantum theory was maybe incomplete in its current form. Maybe there were some things that didn't add up.
Yeah, I feel like hardly any of it adds up to me.
Right? Well, but this paper caused a stir in the scientific community. The New York Times even ran a headline stating, "Einstein attacks quantum theory," even though Einstein himself wasn't a huge leader of the paper. It was mostly written by Podolsky.
So where does the cat come into play here?
Well, we know that Einstein was unhappy with this paper because he says it directly in a letter to his quantum friend Schrodinger.
Oh, Schrodinger.
Einstein and him were kind of pen pals, and they discussed the paper. In one letter, Einstein admitted, quote, "It did not come out as well as I had originally wanted."
Oh, poor Einstein.
I know. You hate to see a disappointed Einstein.
You really do.
The two of them didn't always see eye to eye, to put it simply, and I'm painting with a very broad brush here. Einstein thought that there should be some kind of a way to reconcile the murkiness of quantum theory with the reality that we observe and live in, which is a little bit more binary. Back to your light switch, on is on, off is off.
That makes sense. I'm Team Einstein on this one.
Schrodinger, on the other hand, thought trying to combine the regular world and the quantum world is a headache. So to illustrate this, he made his famous cat thought experiment.
Which is...
Oh, right, yeah. Something about a cat in a box. No, I'm kidding. The thought experiment was that you take a cat, you place it in a box, no one can see what's going on inside the box, but in the box is a very, very small amount of a radioactive substance. It's such a small amount that over the next hour or so, the odds that even a single atom will decay is 50-50. In that box is also a Geiger counter connected to a hammer that is rigged to smash a tiny flask of poison.
Sounds more like Rube Goldberg's cat.
If the Geiger counter detects any radioactivity, it will trigger a relay that will drop the hammer, which will smash the poison flask and sadly kill the cat. Why did they have to pick such a cute animal? I have no idea. So, in the crazy, wacky quantum world, it's possible that an atom could be in superposition, decaying and not decaying at once.
So the only thing that would determine if the atom had decayed or not would be to observe it?
Right. So you leave the cat in the box with all the poison, radioactive junk, hammer, Geiger counter, and you come back in an hour. Now the idea is, if you could extrapolate what's going on at the quantum superposition single atom level up to the cat level, you could end up with a cat that is in itself in superposition. Because it's affected by this long chain of events based on a single atom's outcome. So, in this thought experiment, inside the box, there is a cat that is both alive and dead.
Until you open the box up and see for yourself.
That's when the two possibilities collapse into one, a dead cat or an alive cat. And wouldn't you know it, when I ran this thought experiment in my own head, the cat turned out just fine.
So what was Schrodinger trying to get at with this thought experiment, other than really bumming people out?
His whole point was that trying to rectify the quantum world with our macro world is kind of a farce. He created this ridiculous scenario to illustrate that. There are other problems too. I mean, if you really want to nitpick, some would say that the Geiger counter is an observer since it's measuring the decay or lack of decay of an atom. And even now, people still hem and haw over the little details in this thought experiment.
Yeah, it's still pretty complicated, but I do feel like it gives me a better sense of what they mean by superposition, at least in the theoretical sense.
And it's nice to know that even one of the founders of this field thought it was difficult to understand in our own kind of natural world. In fact, in Schrodinger's later years, he spent more time worrying about regular old biology. He wrote a book called What is Life that inspired a young James Watson, one of the scientists who got credit for discovering the double helix structure in DNA.
So you're telling me even Schrodinger got sick of quantum physics?
Hey, I mean, I get it. We've only been doing it for half an episode and my brain is already starting to twist into a pretzel. So back to the qubits, the bits of quantum computers. They're in superposition. I get that they're not as material as a cat, but they are real physical objects, right? I mean, I'm actually not even sure what a qubit is made of.
Okay, so a bit, like we talked about earlier, is a unit of information, but it can be, and often is, represented or signaled by some sort of physical, tangible thing.
Huh? What? I'm lost.
Okay, let's use an example. think of the light switch again.
Okay.
Now, a light is not really a computer because it doesn't compute things, but it is a binary system.
Right.
It has two states, on and off. Those states are indicated by a little physical switch, and you can assign those states values. You could assign the off position a value of 0 and the on position a value of 1.
Right.
Now you've got this physical thing, a light switch, that's giving you information based on the state that it's in. Does that make sense?
Actually, yes.
Qubits in concept are similar. They are information represented or signaled by physical things. But those things are not as simple as light switches. Often they are subatomic particles. For instance, electrons.
We're finally getting back into the realm of chemistry.
I know, I'm relieved too. Electrons in this instance can be thought of like light switches because they can spin in two directions. Basically, clockwise or counterclockwise, but we call it up and down. Values can be assigned to the direction that electrons are spinning. So like the light switch example, electrons represent a value based on their state, or more specifically, the state of their spin.
So going back to your light switch example, this is like if you took the light switch and made it really confusing and weird.
Yeah, kind of. And also, electrons are not as easy to harness as light switches are. You can go to any old hardware store and grab a light switch and maybe even install it yourself. To wrangle an electron, or a lot of electrons and other subatomic particles, as the case may be for quantum computing, you need very specific conditions. Hard to attain conditions.
Interesting. Why is that?
Well, qubits are highly, highly sensitive. Any kind of energy can throw them out of whack, even heat. Like, almost any level of heat.
Okay, so these computers, they need to be kept very cold, right?
Yeah, and in fact, when you look at pictures of quantum computers, most of what you're looking at, the gold-plated pipes that look kind of like part of a chandelier, that's all there just to cool down the chip that contains the qubits.
I believe it's called a dilution refrigerator.
Right. Well, like I was saying...
Do you ever wonder, what is the history behind the dilution refrigerator?
Do I wonder that? I don't know. No, I don't think so, but...
You should.
Now that I'm thinking about it, I would love if someone could tell me.
Yeah, well, let's go back to 1908. There's a ton of history that leads to these incredible dilution refrigerator devices, so I kind of want to speed round this one.
Okay, doesn't sound like you.
I'm trying something new. With each step along the way, we're going to get colder and colder as we journey towards modern dilution refrigerators.
Ooh, should I get a jacket or?
We'll be moving forward in time, and we'll be getting colder as we go.
Got it.
Let's start with the discovery of something that makes this kind of cooling possible: liquid helium. The year is 1908. Dutch physicist Heike Kamerlingh-Onnes was the first person to liquefy helium at 1.5 degrees Kelvin.
That sounds cold. What's that in Fahrenheit?
It's about minus 457 degrees.
Yikes.
At that time, it was the coldest temperature ever achieved. Kamerlingh-Onnes was obsessed with his work. At one point, his poor wife placed pieces of bread in his mouth to give him sustenance while he worked away at this thing.
Wow, that's ride or die.
But he was so obsessed, he wanted to go even colder. His mission ultimately was to achieve solid helium.
So, like an ice cube of helium?
Yes, like an ice cube of helium.
Whoa.
Sadly, he never got to achieve this dream. One of his pupils produced solid helium in 1926, just a few months after Onnes died. In order to solidify helium, it needs to be not just cold, you also need many atmospheres of pressure. Even heaping on all that pressure, to solidify helium, you need to go less than 1 degree Kelvin. 0.95 degrees Kelvin to be exact, about minus 458 degrees Fahrenheit. At this point, the conversion to Fahrenheit is essentially meaningless because the increments are so small, but we can go even colder.
Colder? How?
Enter the millikelvin. Like the name suggests, this is 1/1000th of a Kelvin.
Wow, okay, so you were not kidding about things getting granular here. That's gotta be like as cold as it gets, right?
No. In
No?
fact, not even close. Our next stop in this journey is the 1950s, where these rare states of helium, of course, are now practically commonplace.
So you go into any corner store in 1950 and you pick up a little helium ice cube?
Maybe commonplace is exaggerating a little bit, but one person who thought a lot about the liquid side of the helium world was a German scientist named Heinz London. Funny aside about him, he helped found the field of quantum chemistry.
So he kind of helped lay the groundwork for quantum computers on both ends then, the quantum side of things and then also with this cooling technology.
Right. London was the first person to propose that a dilution refrigerator was even possible by carefully mixing two isotopes of helium, helium-3 and helium-4.
So he invented the device that cools quantum computers?
I mean, kind of. His idea was about 10 years ahead of its time. It was experimentally realized in 1964 in a laboratory partially named after who else but the guy who made our liquid helium all those years ago, Heike Onnes.
Wow, that's some coincidence. But okay, let's get a temperature check. Now that the dilution refrigerator is invented, how cold are we?
These things can cool an object down to 2 millikelvin.
That's 2 1,000th degrees above absolute zero?
Yeah, that's how cold it has to be to make some of these quantum chips run. Colder than anything in the known universe.
Wow, we are really making progress in understanding quantum computers.
Yeah, I've got the headache to prove it.
Agreed. But I can't help but feel like we're missing an important thing here. Have we actually done any of this stuff? Have we been able to harness any particles that can be used as qubits? And although this quantum chemistry stuff is pretty cool, why does it matter, practically?
I mean, those are great questions. And to help us out, I actually spoke with a reporter who's in a great position to answer these kind of questions. I mean, actually, you could kind of say that he's in a superposition.
Oh, jeez.
Hi, I'm Mitch Jacoby. I've been with Chemical and Engineering News for more than 25 years. I tend to cover materials and energy. In that material subject, I've covered semiconductors to polymers and glass materials, and even quantum dots.
Quantum dots?
Quantum dots are little nanometer-sized crystals of semiconductors. They're called quantum dots because these little specks of semiconductors exhibit some very cool quantum effects. And one of the most easily recognizable quantum effect is their colors. The color of the crystal depends on the size of the crystal.
Okay, so say you had a really nice blue plate. If you dropped it and it shattered into a bunch of pieces, all those pieces would still be blue. But with quantum dots, if you change their size, you change their color. That's pretty cool.
That's why I was so curious about their history. And wouldn't you know it, of course, we only have to go back a couple thousand years.
David, I really do not think we need to go back thousands of years.
Okay, hear me out. Not only is this relevant, okay, but it is also very brief.
I'm starting my stopwatch.
Since ancient times, glass blowers have altered the color of their glass by adding in elemental dust. For instance, gold. When you break it down into teeny tiny little pieces and heat it to a specific temperature, it isn't gold colored at all. It's red. Next time you visit a very old church, look up at the stained glass. Search for the color red. What you're really looking at could be microscopic flecks of gold.
Okay, that's interesting. So we worked with something like quantum dots before we even knew what they were?
Yeah, and stranger still, once we got around to discovering what they were and how to synthesize them, we did it twice, and right around the same time. Both scientists working on this discovery were on either side of the Iron Curtain in the 1980s. On the Soviet side, Alexei Ekimov showed that optical properties of various types of colored glass were a result of copper chloride nanoparticles suspended in the glass. This was in 1981. Ekimov proved that the size of a quantum dot, everything else being equal, could dictate the color of the quantum dot. Meanwhile, over in the States, in 1983, Louis Bruce at Bell Labs proved that those effects could be observed in solutions with free-floating particles, not frozen in glass.
These names are really ringing a bell for me.
Huh, are they ringing a no bell? That's probably because Ekimov and Bruce, along with a third scientist named Muji Bawendi, got the Nobel Prize in Chemistry in 2023 for their work on quantum dots.
Of course, that's right. And if you're interested in learning more about the science behind that prize, you can check out our 2023 Nobel episode.
It's a good one.
Back to our inflection point. So these quantum dots, which can change color based on their size, can be used as qubits in a quantum computer?
Right.
You can take a tiny little speck of a semiconductor, a quantum dot, and if you get the thing unbelievably super cold, you can also control its state. And the state in that case that you're controlling is its spin state. You can put it in the on state and the off state, either one of those, but because quantum dots have this wonky quantum property, they can also be in some kind of a combination of on and off, which doesn't exist in normal materials. And because of that, quantum computers have been, conceived of as these machines that can do unbelievably gargantuan calculations that are impossible for the most super-duper supercomputers to do.
Wow, these dots are versatile.
Yeah, and their versatility doesn't end with quantum computing. I'm sure you've heard of a QLED TV.
No, wait, the Q in QLED stands for quantum dots?
Yeah, isn't that cool?
That is surprisingly cool.
They also have pretty amazing biological applications.
So the deal is you can take a batch of quantum dots and customize their surfaces with some kind of a molecule that's going to latch on to some piece of a cell, some kind of organelle. And then you do the experiment, and you get these things to latch onto where you want them to latch onto. You wash away all the extras that haven't latched onto anything, and then you shine the right color light on these things, and you make these things fluoresce. And you can prove in a microscope that these things have latched on exactly where you want them to latch onto. And then the really cool thing is you could take several batches of quantum dots and customize each one with just the right kind of surface molecule so it latches onto something else. So that way you can light up 3 parts of a cell or 3 organelles in a cell simultaneously, each with its own color. So one thing shines green, one thing shines red, and whatever. And you can watch the way the red thing changes over time while the green thing doesn't do anything, or you can see molecules moving around in cells.
So quantum dots have a lot of neat applications beyond just quantum computing.
I definitely understand why they won the Nobel, and I sort of understand quantum computing, how qubits work, but I don't fully understand why we want quantum computers. What are we going to use them for?
Well, quantum computing could have all kinds of applications, but one of the big ones, and kind of a scary one, is decryption.
Decryption, like code breaking?
Exactly. You see, right now, a lot of sensitive information used online is encrypted. That means it's basically translated into a complicated code. It's to kind of hide and protect the information. If someone else saw it in its encrypted form, it wouldn't really make sense. And to decode it, you would need the encryption key.
Kind of like a decoder ring.
Right, very much like that. Right now, it's really hard to break an encryption without that key. It would take conventional computers a really long time, like more than a human lifetime, depending on the kind of encryption.
Wow.
But quantum computers might change that. They could be so powerful that they might just be able to break that code quickly enough to matter.
Yikes. I'm guessing we're not just talking about someone hacking into my bank account, right? This is national security level stuff?
Potentially.
Okay, and we don't have any of these super quantum code-breaking computers yet, right?
Definitely not. Or not that we know of. There are some quantum computers out there.
Okay.
IBM even offers access to quantum computing online, but none are that powerful yet.
Well, joke's on them. All my passwords are actually written out on handy Post-it notes that I just kind of stick to my computer. So,
well, that's
unbreakable.
That's one way to get around it, I guess.
Yeah. I challenge anyone to try and crack my code.
Is it that one? Is it that Post-it
No,
right
it's not.
there on
Don't
your...
look at that. Don't look at it. That's cheating. Stop looking at it.
It seems kind of short. It's all
Well, okay.
It's all letters.
It's password 1.
I'm really hoping our next topic is a little easier than this one.
Yeah, it is. It's much easier. I mean, the bar's pretty high as far as quantum computers go. That doesn't get much more complicated than that.
Good. Okay. Well, maybe I can actually guess this one from your inflection points?
Maybe you can. Who knows? After conquering quantum computing, I do think that anything is possible.
Okay.
The next inflection points are elephant extinction,
Extinction?
trawling for plankton,
Is that an event in history?
and a man and his wife cooking up corn.
Cooking up a man and his wife cooking corn.
Yeah,
That is,
happened in 1989.
And elephants aren't extinct. I don't even know.
Well, yeah, I mean,
This is,
these are the inflection points. That's just what I've got here in front of me. So
you choose the inflection point.
it's just what I'm reading on the list. That's just what I've got. So,
Who wrote the list?
oh, okay. Guilty as charged, but I promise
Yeah.
I swear, these inflection points will make sense.
Well, it's important that they make sense because this next episode is the season finale, right?
Yep. Lot riding on this.
Exactly. Gotta go out strong.
And we will. I sense you're doubting me, but it's not wise.
So you're saying all of this will make sense?
Every single little bit. The elephant extinction, the
corn?
the corn. Just wait and see.
Okay. I guess I'll just have to trust you. Inflection Point is a podcast project from Chemical and Engineering News.
Chemical and Engineering News is the official news outlet of the American Chemical Society.
Music by Kirk Onstad and Shutterstock.
Cat noises courtesy of my cat, Charles, who was compensated for his hard work with many, many pets.
Written, produced, and hosted by David Anderson and Gina Vitale.
Thanks for listening.